All right, good morning, everyone. So let's get started. I'm going to start already. I won't wait a few more minutes because the AC just turned off. So it's quite warm here. So let's get started with the 8th lecture of the Dark Matter School 2023. So if you're watching this video for the first time, that's a series of lectures concerning dark matter for advanced students, which is being organized by the International Institute of Physics and the Physics Department here in Natal, Brazil. So welcome. And let's start with the 8th lecture. In the previous lecture, we discussed direct detection. And now we're going to finish discussing direct detection, then move on to indirect dark matter detection. So let me share my slides. So we were here in the last lecture. So just to recap, what we've seen was that we derived the formula for dark matter nucleus scattering and showed that how you can connect the dark matter nucleus scattering to the dark matter nucleon scattering. It's just by a simple relation with the reduced mass, one for the nucleus, one for the nucleon or proton or neutron. And you have to, as collaborations, experimental collaborations do, they assume that the coupling with protons and neutrons are the same. And once you do that, so let me just go back here. So you have this formula right there. So the dark matter nucleus scattering depends on the how dark matter couples to protons and how dark matter couples to neutrons for spin-independent scattering. And this reduced mass is reduced mass between the dark matter and the nucleus. So mu here is the product of the dark matter chi mass times the mass of the nucleus divided by the sum of those masses. This mu here is the dark matter chi nucleus. And it wants to, what the experiments report is not the constraint on the dark matter nucleus scattering, but rather the constraint on the dark matter nucleon scattering. So what they do, they assume that Fp is equal Fn, so dark matter couples to protons and neutrons in the same way. In this case, then the Z dependence goes away, and you have just a Fn squared A squared dependence on the that governs the dark matter nucleus scattering. And when from this one you convert to a dark matter, let me erase here, to a dark matter nucleon scattering cross section by simply you have this one, so you get mu chi n over pi squared, and then you get an Fn squared A squared. So that's what you get for dark matter nucleus scattering cross section. And then for a nucleon is simply mu chi n nucleon pi Fn squared. And then you integrate out the A squared dependence. So that's what the dark matter nucleon scattering cross section looks like. So this thing is just particle physics, as you can see. So it's just how dark matter couples to up and down quarks, and then eventually you translate that to dark matter nucleon scattering. Okay, so there are two conversions that need to take place. One is from quarks to nucleons, from nucleons to nucleus. Okay, but luckily our nuclear physicist friends have done this for us, and the only thing we need to do is to plug in the numbers once we know our model. Okay, and now I want to show this one, this figure, which is the common figure where you're going to see at conferences, where direct detection experiments, they report their new results, no results so far. And this figure, I'm going to try to explain some key things. So you've learned already from last lecture that the reason why those curves have this shape So they go up, they rise up for low dark matter masses, and then they have a dip, and then rises again linearly with the mass, with 1 over mass. Okay? So this has to do with the energy threshold. This has to do with the kinetic arguments, okay? Reduced mass of dark matter between the dark matter particle and the nucleus. And this has to do with the 1 over m chi behavior, which is related to the number density. Remember, rho is n times m, but the scattering rate depends on the number density. Therefore, the number density is rho over m chi. So as I increase the dark matter mass, the number n chi decreases linearly, 1 over x m chi. Then the scattering rate decreases, and as the scattering rate decreases, my constraining power weakens at the same rate. So I have 3 features: threshold, kinetic arguments, and kinematics, and the number density. So one has to do with astro, one has to do with just relativity, I would say, kinematics, and this to do with detector. So, and then you see that all the direct detection experiments have the same feature. Their limits have the same feature for all of them. They have different ways, different limits, obviously, but they have the same shape. And the reason for this, as I'm going to cover now, is for this reason. Hold on. So, as you know, the rate dr dE is proportional to the scattering rate, and also goes 1 over the mass, dark matter mass. And also you have some form factors in the velocity distribution of V. Okay, but we also had a number here in the numerator, which was the number, oh no, sorry, and the number of targets, which is related to the exposure, okay, the volume of my detector. So as I increase the volume of my detector, my constraint becomes stronger at the same rate as I increase the volume of my detector. It's linearly dependent. So as I scale up the volume of my detector, the number of targets, I increase my constraining power, okay? Therefore, these detectors, they need to go bigger, grow bigger and bigger and bigger. Because as they grow bigger, much bigger, and then my limit or my sensitivity to that scattering grows linearly. So and then for this reason only, you see that these detectors which have limits way down here, that's happening simply because they went from one fiducial volume to the other. Okay, we're just increasing the fiducial volume of the detector. Fine. Okay, so that's why you can move down by scaling up the volume, the fiducial volume. And the reason why some detectors have a curve like this, and then eventually they have a curve like this. So the reason why it moved down is because they increased the volume. The reason why now they're covering lighter dark matter masses is because they got a better way to reduce the energy threshold. As you reduce the energy threshold, you can cover smaller masses. Remember? Because this energy threshold dictates the smallest mass you can probe for a signal. You can probe in a given signal. Okay? So that's the way you can move. You can move downwards or to the left, and then has to do with the energy threshold and the volume, fiducial volume of your detector. Obviously, you can also scale down if you have a better handle on the background. Okay? If I control more my background, my constraining power becomes more effective. The more I know about my background, the more the better the constraint I can get on dark matter scattering. Make sense? Okay. And as you see here, what I have in the x-axis, now let's discuss in more details, is the dark matter nucleon scattering cross-section, and the x-axis we have the dark matter mass. So you see now we are probing, so this xenon and ton, which was the latest limit basically, and LZ, this is the projected limit, okay? The xenon now is today's current, so this one right here, around there. It did not go as good as they projected, but it's similar to this bound for cross sections around 10 to minus 46, which is roughly what they probed for dark matter masses between 10 GeV and 100 GeV. That's in GeV units. So they probe cross section around 10 to minus 46 centimeters squared, or 10 to minus 10 picobars. So I want to point out some important things. So first one is that you see that there is a large portion of parameter space which is not covered towards light dark matter masses. This has to do with the energy threshold of those detectors, because the dark matter particles became too light to produce a detectable signal. And because of this, new techniques are arising now, because they want to cover the whole parameter space. So how can we overcome the energy threshold of direct detection experiments and then cover light dark matter particles masses? How can I cover light dark matter? The way they do it, there's many ways. One of them is using different targets which have lower energy threshold. That's the easy part. The second one is just remember that most of those detectors, they require ionization scintillation, for instance. And having a second readout technique makes them harder, makes the energy threshold those detectors increase. Because what happened is, remember that the case of cogent we discussed with cogent had just ionization, and the energy threshold of cogent was really small because they had just one readout techniques. And it means is ionization is very efficient. Ionization refers to the amount of electrons that I get when something comes in, hits the nucleus, and strips off some electrons. That's the ionization. You ionize the atom. This requires a very small energy threshold, because for most of the detectors, we are talking about EV ionization energy, KV ionization energy. So it's very small energies. So then I can really lower the threshold if I rely just on ionization. In some of those experiments, what they did was they gave up on the idea of having a second readout technique. Once you do that, you pay a price, which is you don't know so well the background because you're paying a price. Because with two readout techniques, you have a better handle on the background. But you gave up on that at the cost also to probe lighter dark matter particle masses. Okay? But then it's tricky now to distinguish signal from background, because you don't have two readout techniques. Because remember of the xenon we had, the xenon was the time it takes for S1 and S2 signals to appear is one of the ways how they can distinguish signal from background. But there is not just S1 and S2, there's just one S1. So now how are you going to distinguish a signal from background if you have just S1? So they have to really know really well the background to say, look, I observe, sorry, I expect this number of events from background. If I see something more, it's a signal. They have to have a very good understanding of their background in order to claim any dark matter signal, the observation of any dark matter signal. So it's tricky in this sense, but some experiments have given up the second readout techniques to then be able to cover light dark matter particle masses. And some other ways are to use different targets, which has the material itself has a lower energy threshold. Okay, and light targets, because the lighter it goes, the less is the minimal velocity I need to produce a signal. Remember? So for instance, everything is related to reduced mass. So as I increase, if I have this is visible. Let's say I have a ball really heavy. Comes a light dark matter particle, hits the heavy ball. Well, the energy for me to see any vibration on this ball is tricky, right? Because it's a heavy ball, it's a heavy nucleus. And the light dark matter comes in, it won't produce any visible signal. But as this ball becomes very small and light, if a light particle comes in and will bounce this thing, and I'm going to see it because it's bouncing, because I reduced the mass of the nucleus. So as I go to lighter targets, I'm becoming able, just from kinematics, of increasing the chances of observing a signal, right? That makes total sense. Then on top of that, if I use these balls or detect materials which have a low energy threshold, from going from the valence band to the conduction band, or the ionization energy, the energy requires to strip off an electron, then I can probe again light dark matter particles. Okay? The smaller the energy, it means the smaller the mass. Because the dark matter energy it has is just kinetic energy, mass v squared. Right? So the mass I already know is the same for all of them. It's a Maxwell-Boltzmann. The only thing I can change is the mass. Okay? Okay, fine. So another thing I want to discuss in this plot is the neutrino floor. So the neutrino floor refers to a irreducible background coming from neutrinos. So this part here, this corner right here, is solar neutrinos. So these solar neutrinos are well measured, and they come either from beryllium or from boron decays, and they produce neutrinos. They always produce neutrinos if we detect them. But the neutrinos are coming to us all the time. However, that cross-section is small, okay? It's small, around 10 to minus 44 for this mass. So what are you saying this orange dashed curve is the following. What would be, so I know the flux of neutrinos coming. Okay, I know the cross-section, it's standard model physics, right? There's nothing new, it's standard model. Okay, knowing that these neutrinos are coming towards us, they're passing through the Earth because they are weakly interactive massive particles, right? Interacting massive particles. They're coming to us. The cross-section I know is standard model physics. What is the signal they produce in my detector? They produce this number of events. This number of events is small. Well, if I'm trying to probe this region here in blue, then the number of neutrino signals they produce is small because that cross-section is small, 10 to minus 44. Okay? Because the smaller the cross-section, the smaller the amount of events they yield, right? So I'm probing here. But as I push down the sensitivity of my detectors, as I'm going down, I was here probing here, and then I'm probing there, and then I'm probing here, I'm probing here, and then eventually I'm going to probe there. But now as I'm trying to see a signal which is roughly producing a cross-section similar to neutrinos. But now comes the question, how do I know if that signal was produced from a dark matter particle, whether from a neutrino? Because the signal is the same. Is a neutral particle, comes in, does interact strongly, weakly, and just scales, does not have electric charge, just scatters off a neutron, bounces, strips off some electron, and I measure these electrons. So how do I know? So you can't know unless you knew in which direction that flux of particles was coming from. But that's not easy. They are neutral particles. They do not interact strongly. So it's tricky to measure where that particle was coming from. Why? Because the flux of neutrinos from the sun, I know in which direction it's coming. It's coming from the sun. Dark matter is around the whole galaxy. It's not coming just from the sun. So if I know, if I somehow can deduct in which direction the flux was coming from, then I can potentially separate neutrino signal from a dark matter signal. Okay? So neutrino floor is irreducible, so you cannot remove it. It will be there no matter what. So the neutrino floor refers to a reducible background from the standard model, which mimics the effect of a dark matter recoil. Okay? And that comes from the sun, this one in the corner left, and this one comes from atmospheric neutrinos, and these DS and these supernova neutrinos. So you have solar, atmospheric, and supernova neutrinos. They'll always be reaching us, no matter what you do. We've measured them already. That's why there's a line there. We measured. Therefore, as you can see, these experiments are like, let's say, 2 orders of magnitude away. But as we move down the sensitivity, at some point, we're going to be probing cross sections that will be like this red line here. And then, okay, and how come how did you arrive at a limit like this one? Because this one, you are deep inside the neutrino floor. Okay, so if in order to do this, you have to know really well yours, because you're saying, look, I observe some flux. Because remember, what they do is I observed, let's say here, I observed the number of events here, n, which is number of background, let's say background events, plus number of events from dark matter, plus number of events from neutrinos. But I'm here in the red region. How do you know this is neutrino signal or dark matter signal? You can't know. You can't tell them apart. Because if you are here, remember, if you there say, okay, I observe this number of neutrino events, but the measurement we have for neutrino flux down there is not so precise. There's some error bars. So if you observe, the number of neutrino flux is huge. It's really big. So let's say you observe 10,000 events, but from dark matter you expect 2 events. So you will always be within the error bars of the 10,000 events. So it's 10,000 events plus minus 100. So the dark matter signal could be buried in this error bar, and you wouldn't know. So that's why now you limited the sensitivity of the direct detection experiments of probing any dark matter signal, because the dark matter signal will be buried in the neutrino floor. That's the way they quote. Oh, the dark matter signal is buried in the neutrino floor. Okay, está enterrado, is buried in the neutrino floor, because you just can't tell the difference. Good? Any questions?
I always thought about that. I mean, what is the dark matter section as a function of the dark matter mass? In the case of neutrino floor,
they are placed in the neutrino nucleon scattering cross section as a function of the energy.
Oh, okay.
Yeah, sure. Yeah, they have to convert into energy. And the energy of the dark matter I know in relation to its mass. So that's why this line here is not really at face value line, because the velocity of, for instance, let's say the energy of the dark matter is mv squared over 2, right? But v is not fixed; it's a velocity distribution. So it's, in order to convert neutrino and dark, relate these two things, right? So that's the energy of chi, and the energy of neutrino is just the neutrino energy. But I want to convert this thing back into this one, so I have to know the velocity, right? If they're the same. So let's say now I make E chi equal E neutrino. Then I have m chi v squared over 2 equal E neutrino. Then I know the neutrino energy. So, but what is the velocity you're gonna choose? This is the velocity distribution. So that curve alone is not a really at face value curve. There is some error bars. And there are some other things that I didn't mention, is that so as you said, for instance, I said in the very beginning, this neutrino floor is governed by standard model physics, right? That's what I said. But if it is not, And then Ricardo is saying, which sense, right? So let's think of the following. So let's think of an interaction. So this interaction for neutrinos goes like this. A neutrino comes, finds a nucleus, exchanges the Z boson, the neutrino continues, and then the nucleus is there. So that's a neutrino nucleus scattering, okay? Fine. However, if I have this, so the cross-section for neutrino can increase a lot. If this guy is much lighter than this one, which cross-section is bigger? This one, right? Because remember, it goes with one of the mass of the propagator squared to the fourth power at the end. So if I have a new vector boson, which is lighter than the Z boson, then the cross-section for neutrino nucleus scattering is much higher. If it's much higher, means that instead of this curve being here, will be around there. So it means is at the end that even the current direct detection experiments might be sensitive to new forces in nature. So they are maybe underestimating the number of events because they should have included the events coming from neutrino scattering, but they did not. Okay, they underestimated the new physics contribution because the new physics for them is not just dark matter. That could be also new force.
This is for dark matter detection, direct detection. So are there any experiments that detect only neutrinos?
There are.
That wouldn't detect dark matter at all?
If there are, no, we have detectors just probing neutrinos.
Yeah, but these experiments, dark matter would be detected, would interfere if the was
but
there.
I know, but in this case here, the one I just circled, there is no dark matter whatsoever, right? This one, there is no dark matter. This one, there is no dark matter.
Yeah, I know. I was asking because there are neutrino experiments, neutrino direct detection experiments that are not sensitive to dark matter. Wouldn't we know if that was there or not?
If there are experiments that can distinguish between dark
matter and neutrinos, like it's only a neutrino experiment, direct detection from.
Yeah, they only see neutrinos then.
Yeah. Wouldn't we know if that cross-section, that scattering was possible from that experiment?
Yes, but the constraints are not as restrictive as those from direct detection. So, for instance, we can probe we can place limits on new forces using ice cube neutrinos, an ice cube detector. We can also probe. There's another one called Antares, which is the same. I mean, we have others, Chemi3Net. We have Super K, Kamiokande. We have neutrino detectors just meant to detect neutrinos, and using the neutrino flux, they measure. They say, look, observe this number of fluxes of neutrinos. If there's a new force coming in, so then the flux should be different from the one I measured. Then I place a limit on the contribution from the new physics. Okay, but the level of precision they acquired is still far from those from direct detection experiments.
So we cannot rule that out.
No. Okay. Okay. And even the cross section itself is very different. The one we are talking about a neutrino interacting with a neutron, with quarks. The one that they measure at neutrino telescopes are using just charge current. Neutrino, an electron, and a W boson. It's just based charge currents. And the lights they produce are different, bluish or less bluish, depends whether what's producing a muon or an electron neutrino.
Well, I mean, that neutrino electron scattering, for example.
Yeah, but he's asked about neutrino experiments.
But I mean, because it would be something that kind of mimics dark matter in the sense.
Yeah, for neutrino electron scattering, that's a different thing. Then you could also place a limit, but the bounds from neutrino electron scattering are much more restricted actually than these neutrino nucleus scattering. But still it's different. Neutrino electron scattering. This is neutrino nucleus. So it's you in here you're probing a coupling between neutrino and quarks. Okay, that's what you're probing. The one for neutrino telescopes, they're probing just the charge current in the leptonic sector. That's not the whole story, because there was a new result came from a collaboration called Coherent, which measured the neutrino nucleus scattering for the first time ever. They measured this in 2017. Okay, so the lesson is direct detection is tough business. Okay, it's very tough. Is there any question from this slide? No? Okay. Hold on, let me erase. What's that? Okay, so they're just saying, for instance, this was from someone's lecture. Say, hey, my favorite model lies in this bubble, in this ball. Okay. That's what it is. So one thing I should emphasize also is that I'm glad for your question because of this. Now I remember something. So typically, people thought that dark matter, WIMP dark matter, would appear somewhere around here. So that's where the region for WIMP dark matter would appear, around there. So that's the, I'll say, is the vanilla, the expected region where you see a signal. If you haven't seen so far, okay, there are 2 orders of magnitude still to cover, but you haven't seen any. And then people start realizing, revisiting their assumption about thermal production of dark matter. Was really dark matter thermally produced in the early universe? Was dark matter coming just from the abundance, just computing the Chi bar, going to fermion, anti-fermion? What could be something extra? Could be other channels being producing dark matter, contributing to the dark matter abundance. Could be non-standard cosmology, something beyond lambda CDM, something extra, some extra cosmology would change the Boltzmann equation. Yes, would change the Boltzmann equation. Where those regions, favored regions, would locate if you start changing your premises. And then they realize that as you change your premise, then these favorite regions could be around here, could be around there, could be around here, could be around there. And then you don't have now a fixed favored region. So this region for WIMP, which is just historically speaking, is just a region where people from supersymmetry expected dark matter to be. So this, what people refer WIMP region, actually you can just remove it, say SUSY expected region. That's what it used to be. So the WIMP searches were really heavily driven by WIMP, by SUSY. So to have an idea how seriously the American and the European community takes the dark matter search is the following. So DMSM, the minimal supersymmetric standard model, does have a dark matter candidate called neutralino. Okay. The moment at which the direct detection experiments reach a cross-section which removed the neutralino to be dark matter, they gave up on the MSSM. MSSM cannot be the theory because the neutralino is excluded. Because there must be dark matter. If MSSM is not a theory, so it has to be an extended MSSM. They came with another one, PMSSM, MSSM, next MSSM, changing the supersymmetry to accommodate the dark matter limits. So they are changing their theory in order to have a successful dark matter candidate. Okay, so that's how seriously they take the dark matter events. but they were also biased in some way because they expected the signal to be there. But doesn't have to be true. If you separate now dark matter from supersymmetry, because dark matter is, the evidence for dark matter is much more compelling than supersymmetry, which is none today, according to data, right? There is no data favoring supersymmetry whatsoever, none. There are theoretical arguments, but no data. And for dark matter, we have data. Okay? And then if you separate those two, then one has nothing to do with the other. Then you can have dark matter candidates, which has nothing to do with supersymmetry, which can have different regions where the relative density is correct and doesn't have to be within the first ellipse that I drew in here in this region right there, this one, this big one. Doesn't have to be there. It can be scattered in different places of this plane. Okay? Any further questions? No? Okay, I think I'm done for this 7 lecture. Yes. Before I move to direct detection, let me cover something that I haven't covered before. Still in the aspect of direct detection. So you can see in this paper, what it is about people have simulated the formation of our galaxy using dark matter particles. And one thing I haven't told you is that the density of dark matter in a galaxy is related to the velocity distribution of dark matter particles in the galaxy. So velocity distribution is not disconnected from the density profile. They are related. Actually, you have to feed in the velocity distribution to get the dark matter density. Well, it's sort of reasonable because you have to know how these dark matter particles are moving to predict where they're going to accumulate and form structures. Okay? So one is connected to the other. But in order to have a density profile that fits the data we see in galaxies, we see the stars moving with some velocity, galaxy rotation curves, and so on. In order to fit the galaxy rotation curves, the velocity distribution you have to fit in your simulation is a Maxwell-Boltzmann, close to a Maxwell-Boltzmann. So the data from the distribution of dark matter in galaxies is telling you that the velocity distribution of dark matter particles to form a galaxy has to be close to a Maxwell-Boltzmann distribution. And the paper one of the first papers that discussed this is this one. So back in 2009. And first, now let me show you that our community is very different from others. This is a well-known paper. And this well-known paper was published in JHAP, not in Physics Review Letters, not in Nature, is in JHAP. It's a well-cited paper published not in Nature and not in Science and not in Physics Review Letters. Okay? So what they discussed was what is the impact? Could be the velocity distribution of dark matter be non-Maxwellian? Could be different from Maxwell-Boltzmann distribution? That's what they're trying to assess. They were motivated by something which is called the Dama modulation, but I won't have the time to cover this. But let me show you something. So they used 2 simulations. One is called, hold on. One is called Via Lactea, and the other one is called Gallo. These 2 numerical simulations of galactic dark matter structure. So now I'm going to show you the picture. Before I show you the results, let me show you the picture of them. This one. So this is the paper I just showed you. And this paper, which is on our arXiv, they had a supplemental material, which is this figure. So that's the figure they got from the simulation. Okay, it's quite nice. And I was searching if they had a video for that simulation. They don't. Or maybe they didn't make it public. Okay, so nobody can steal that data or something. And however, I'm going to show you something that means the same thing at the end of the day. So this is a dark matter simulation. So they So every single point of light you see is sort of a solar mass-like dark matter particle. Every single point of light. So it's like a galaxy with 10 to 14 solar masses, which is our Milky Way. Our Milky Way has 10 to 13, 10 to 12. I don't remember now the number, exact number. 10 to 12 solar masses. So there are 10 to 12 dark matter particles of a size of a solar, of the sun. And then they assume that just gravity takes place, and there is a perturbation, the density, consistent with the one inferred from CMB, and let it grow. And the point is, let it grow, and then they see the final result. They see the final result compared with spectroscopy measurements of the CMB of the Milky Way, and compare the two photos. And just from the two photos, they do a statistical analysis to see how close they are to each other, and how long it took for the simulation to reproduce that Milky Way. The time it takes matches the age of the Milky Way. Obviously, they don't like to take millions of years, right? But it's somehow normalized. It matches the age of the Milky Way, and the two figures, two plots, they agree with each other. Just letting dark matter take place. And here's like the condense that will turn out to be the center of our galaxy. As you see, some of them are moving away. So let me speed up. That's the brightest, that's the center of our galaxy. Let me show you another one. This one is this one is old, but it's the one that I saw on YouTube. So it's a smooth halo, see? It started with a smooth halo. You don't see it's like uniform at the beginning, but the homogeneities are very small. Then they start clumping. And that's the time here in giga years, see, on the top? Look at the size, that's in 500 kiloparsecs. So this one is not from one galaxy because 500 kiloparsecs is like our universe. In every dark spot, well, very bright spot you see is a galaxy, basically. So this is just a simulation. Okay, I guess this is now. This millennium was the famous one so far. Let's see. They travel through space, man. It's very amazing. You know what's funny is that, for instance, you saw these filaments of structures, right, really bright. And the size of these filaments are the size of the filaments we observe in the universe today, using a simulation, and it's pretty amazing.
When I see this person like that, these filaments, they look like neural networks and stuff like that. They interact with gravity, right? Why don't they like clumps like our ordinary matter, like spheres, like planets, and
Because at some point, the non-linear regime kicks in. It's not linear, it's non-linear. So you cannot just assume there'll be a spherical thing and so on. We don't know. So predict the formation of planets is highly non-trivial.
what? Sorry?
To predict how is the formation of a planet is non-trivial because the scale is too small. At very large scales, the universe is isotropic and homogeneous. But as you decrease the scale, then the nonlinearity becomes so important. That's how you can scale down and take into account all these nonlinear facts at low scales. We don't have the computing power and knowledge to do so. And why the planets look sphere? And I'm not the right person to answer that. Anyway, so what I want to show is that these cosmological simulations show that the dark matter distribution should be close to a Maxwell-Boltzmann. Now I'm going to show you the plot they have. So that's a very famous plot. Let me show you this one. So you can see here in the halo rest frame, this is like this dotted, oops, that's 14. Yeah. So you can see this one, for instance. They have different simulations called S, Gallo, blah, 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 VL2. For instance, the dotted one would be the Maxwell-Boltzmann. See? It has a reasonable agreement with the simulation. So you see here and this one here. But what they're showing is the simulation showing that in some cases, the Maxwell-Boltzmann distribution seems to be too spiky compared to what we actually see. Okay? So maybe we are overestimating the highest velocity we have for Maxwell-Boltzmann compared to what real data, mock data would look like. No, this one's just, you're just changing the frame. Earth frame and halo frame. So it would be from the sun location. Then we have a different velocity towards the halo, right? So it's smoother when you at the Earth frame. Anyway, and then they all point to a velocity. You see the most likely velocity is around 200 something. For instance, at the sun location is around 250, basically also like close to 250, 240, something like that. So that's the average velocity will be around this. When you take the average velocity of integrate in the Maxwell-Boltzmann, you get 200 something, 250. Integrating from V min to V escape. What?
So the experiments are taking here, so
Yeah. Yeah, so the Maxwell-Boltzmann has a very good agreement, see? Since we have detectors are here, what he's saying is that detectors are here. So it's as detectors are here, and the Maxwell-Boltzmann fits pretty well what the mock data tells us, right? So, and then there's another thing. Why they were discussing this? Well, they were not interested in this, actually. They were interested in trying to address something called inelastic dark matter, which is something that I'm going to explain now. So let me go to... So here they just relate how the number density, the halo profile, is related to the velocity, and they compute the whole thing. But let me discuss something else. Hold on. Implications for demo here. So let me discuss. Let me go back to figure slide 7, because we're still in direct detection. The way it goes is the following. Okay, so we had a dark matter particle coming in, hits a nucleus, and then the dark matter goes, and the nucleus is there, scattered nucleus, and star. Okay? All right, so look at this. So let's say this is the particle physics stuff. At the detector level, I have an energy threshold, right? That's what it means, energy threshold. Now let's think of the following. So the detector is still the same, the target is still the same. Comes the same dark matter particle here. But in my model, my particle physics model, this chi and star does not exist. In my model, what I have is chi1, then chi2. I have two dark particles. And I'm going to assume that chi2 is minus chi1 is equal delta. So and chi2 is heavier than chi1. Now, pay attention to this. In order for this scattering take place, okay? In order for this scattering take place, this seems to be not kinematically possible, right? Because chi2 is larger than chi1, okay? But actually, it can happen if m chi2, for instance, I come with a chi2, comes here, kicks in, and then the velocity of chi1 turns out to be larger than the velocity of chi2. Okay, to compensate, because it's not just the mass as the energy, right? The energy has to be conserved. That's fine. But as long as V1 is larger than V2, then it's okay. I compensate for the mass difference. Fine? So this model where I have chi2 heavier than chi1 is called inelastic dark matter. Has nothing to do with the scattering being elastic, as like being deep into the nucleus. What we refer by elastic is just bump, you see the whole thing, the nucleus as a whole. And elastic is when my wavelength is too small, and then I can see the whole nucleus, right, inside. I see the nucleus. That's called inelastic, deep inelastic scattering. Inelastic means I see the whole thing inside. Let me just close this WhatsApp. In this case, inelastic dark matter refers to the case where I have two dark matter particles, one is heavier than the other. But look at this. This velocity of V1 has a maximum value, right? It cannot be anything, limited by the Maxwell-Boltzmann distribution. Okay, so look at this. If I go to light dark matter particles, very light dark matter particles. Remember, if the dark matter is very light, let's say 1 GeV. M chi is 1 GeV. And then I can see a signal. If dark matter is 1 GeV, let's say I'm right there at the threshold of observing this scattering. And then I can see it. If dark matter is lighter than 1 GeV, I cannot see it because the energy deposited is smaller than my energy threshold. Okay, it's small. I can't see it. It's very hard for me to see it. There's a velocity distribution, but it's still very hard for me to see it. Fine. Then look at this. If I go to the, then you get a different target, heavier target. The heavier target, assume the energy threshold is the same, you would definitely not see that signal, right? Because remember, the energy threshold is the same for those. I'm assuming to be the same. Simplify my reasoning. They have the same energy threshold. I have a light target, I see it. A heavy target won't see it because the energy deposited will be very small because it increases the mass. Make sense? Fine. Now let's go to this complicated case. I have chi1, M chi1 comes in. M chi1 is light. For me to see a signal, that velocity of chi1 has to be at the tail of the Maxwell-Boltzmann distribution because it's too light for me to see it. So only the events, the particles that are at the tail of the velocity distribution will produce a signal for me, right? And then imagine for a target which is heavier. No way at all they're going to see a signal because they have a heavier target, right? So then, in order to ensure that the other detector won't see a signal, what I do is I assume that my dark matter particle is not just one species, it's two, chi1 and chi2. And then for this event, chi1 here produce a chi2, V1 has to be larger than V2, right? So I have to be really at the tail of the velocity distribution to produce a signal. So I'm forcing my signal to happen at the tail of the velocity distribution. And then in this case, I can make sure that a heavier target will not see a signal whatsoever. Because there is no velocity larger than how it's going to see a signal, V1. Because V1 has to be really at the tail to see a signal, right? Okay? Obviously, there is a game here between the mass and the velocity distribution and so on. But this idea of inelastic dark matter came, why this was proposed? Because Cogent had observed a signal. And also, even before that, Dama also observed a signal, which was consistent with WIMPs, measuring scattering, nuclear scattering of WIMPs, before Cogent appeared. And the regions where you could explain the Dama signal and the Cogent signal, they overlap. And they favor light particles. And people say, okay, but how can you explain xenon is not seeing it? People said, no, but you know, it's a heavier target. It's a heavier target, so you need to be at the tail. And what people said, okay, let's be now at the tail, near the tail. The velocity, I picked the velocity to be, the mass to be 1 GeV. And only particles at the tail will produce a signal. If this is true, how xenon is going to see a signal then? Because there's no velocity larger than the tail. Make sense? So let's say I'm at the tail, right? I'm right here. So let me draw the tail, the Maxwell-Boltzmann distribution. And I'm picking a mass so that just this contribution of the tail, you produce a signal. I'm right here. So this one will produce a signal that I can see. So any heavier target will not see a signal because they would need a velocity higher than this one because they have a heavier target, but there is no velocity higher than this one. then it's a way to make sure that explain why, definitely, conclusively, why heavier targets have not seen a signal consistent with those observed at Cogent and Dama. And to make sure, even by kinematics, was this inelastic dark matter. And what I'm going to show you here is the Vmin, the minimal velocity you need to produce a signal. So you need the minimal velocity as usual, but there is some delta. Delta is the mass difference between chi2 and chi1. So as you see here, for instance, the mass of the target is mu is the reduced mass. So it means is as soon as I increase delta, I increase the mass difference between chi2 and chi1, the larger the velocity I need for V1. V1 has to be larger and larger. Just look at the figure here. This one. So for this guy to produce this one, V1 has to be larger than V2. And as I increase the mass difference, the larger will be V1. But as I increase and tune the mass difference, I reach a point that V1 has to be larger than the escape velocity. So I'm just making it impossible for other targets to see it because I tuned the mass difference to be so that V1 has to be larger than the escape velocity. Make sense? And that's a tuning, it's a fine-tuned model. Okay, it's not something, okay, that's very natural. But it's a tuned model to explain why some of the detectors have not seen a signal and the others have had seen a signal. So that's called inelastic dark matter. Was proposed by Neil Weiner. He's a professor from University of New York, NYU. So that's inelastic dark matter. And then let me see if they have the figure here. Let's just show you when you take that into account. Where is it? Here. Look how fine-tuned it is. So they changed delta, the mass splitting, and now there is a region here which survives the limit. It's really fine-tuned. See, because those limits are excluding everything to the other side. So as you go to heavier, let me see this one. Yeah. This one, let me see. Let me see what, there's one which is clearer than this one. Okay, no. It's here. Okay, there is more visible. Yeah, so now they're picking different masses. As they increase the mass, the limits decreases, and then they go, see, here now you have a whole region, which is okay. And then there it goes, many masses and so on. Now, for instance, this one's more clear because they're scattering cross-section. For instance, in this case, okay, it's clear. So look at this. So this is the scattering cross-section where everything above the scattering cross-section is excluded, right? So you cannot have, any event above. So now they're picking the mass and say, look, if you want to explain Dama and Cogent, let's say you have to be within this best fit region. In this case, so far, there is no inelastic dark matter. So I see, let me see. No, they just take a V velocity and so on. Let me see if there is one. Yeah, it's not there. Anyway, I think the message was clear. It's just they want to tune the mass difference to make sure that the xenon signal, the Dama signal, still survives the xenon limit. And there is another discussion which I mentioned to you, I think 2 lectures ago, which is they take this limit from xenon and move to the right. So he appears right here to survive some region there. Based on what argument? The fact that xenon did not know really well the quenching factor. So they overestimated the quenching factor. But this has been driven the community for 2-3 years. But as xenon improved its sensitivity, said, look, man, you can come up with quenching factor, tune the velocity, inelastic dark matter, I don't care. It will be excluded anyways. So the message to conclude the direct detection part is, we observe cogent was very important, provided us a very important lesson. And Dama did see a signal from dark matter. The significance, well, did see a nuclear recoil signal. Doesn't have to be from dark matter. And the significance is over 9 sigma. So 9 sigma confidence level. Dama observed a 9 sigma confidence level signal. And the signal they observed was modulating in time. Why this has anything to do with dark matter? Well, we are at the sun. The sun is moving in our galaxy. It's moving. However, the Earth is also translating, right? So at some point, the velocity of the Earth goes in the same direction of the sun. Sometimes it's moving in the opposite direction of the sun. So it means is half of the year, the Earth is moving towards the sun, the same direction of the sun. The other half is moving the opposite direction. Okay? So it means is there is a modulation signal. I mean, remember that the rate depends on f of v. So f of v is actually, that is a velocity, is a vector velocity, not just the module. So at some point, this velocity goes in the same direction, they sum up, and some half of the year, they go in the opposite directions. Okay? So you have a summer and winter different velocities. So you have a different flux or rates of nuclear recoils depending on the season of the year. And this has been measured from Dama with a 9 sigma confidence level. And that has been making the community crazy. Is how can you see a 9 sigma signal and is modulating? There is no well-known background physics that will modulate in time. None. And then people realize that muons from the sun, they modulate in time. But they do not modulate in time with the same season, summer and winter modulation phase. It's different. The sun cycle has a different cycle from the Earth's translating period. It's not the same phase. We have in April, they have in the summer and winter. And the one from the muons from the sun, cosmic ray muons from the sun, are different. One. The second is they didn't realize what it was. They built different detectors, direct detection experiments called cosine, there were others, to test using the same materials as Dama, made of sodium and iodine. This one. Sodium and iodine, to test if it could also see a signal. They see a modulation in the number of events. They did not see a modulation in the number of events. And then people say, okay, maybe it's the location where Dama is, because Dama is in Gran Sasso. But Xenon is also in Gran Sasso. If you remember the picture, they're basically one close to the other. Let's see if it's here. It's in the 6th lecture. They were in the same lab. I mean, a few walls away. So it could not be the location. Maybe, I know, maybe some stream of dark matter is hidden in Gran Sasso laboratory. And then what people realized, that's the most accepted answer to the modulation of signals observed at gamma, is that the electronics they have, for some reason, is leaking into their detector and producing a modulation. And weird as that is, there are some nuclear materials which do modulate their decays. That was not known. They just realized this. And for some reason, gamma is not a dual phase detector. It's not even a single phase. Gamma just counts the number of events, and that's it. They have a tank of sodium iodine and detects the number of nuclear recoils and just count. And they count the total number of events, say, which ones are modulating time? These ones. They are not, the others are not modulating, so throw them away. So they do not distinguish whether the event was coming from dark matter, from nuclear beta decay, whatever. They just sum them all. And people are placing doubts, hey, okay, so since this is so important for the community, could you show us your data, your raw data? No, we won't. So let me test your hypothesis to see if you didn't. No, we won't. And then as they are not publicly showing their data to the community, then their results were not taken so seriously. Because if you're confident about your result, this experimental result, you should be able to make your data public. Okay? Because that was like, remember, if they did observe dark matter, they get a Nobel Prize. Is a Nobel Prize worth attitude? If they show it's there, the Nobel Prize. So why didn't you want to show it? And they haven't shown ever. And they have been observing a modulation signal since 2000, I believe. Up to this point. So let me just, I end up just talking about drug detection. So I just wanted the next 15 minutes, just start warming up for indirect dark matter detection. And because I'll have to leave soon enough. And first, let me ask, is there any question so far? No? Someone there, back there? So our girls are back, so I'm not gonna ask the other girls. We have other girls there, so anyone? So Ana, Guillermo, Mikael, in the chat. Are the limits similar for axons? No, they're not similar for axons because axons have a different velocity distribution. Well, axion dark matter do, but not other axions. So let's just warm up regarding direct detection of dark matter. So let's review the assumptions. So the assumptions I want to emphasize is that first, we are not probing the thermal relic, okay? Number one, we are not. But you're gonna see in papers, and maybe tomorrow, if they're paper, you're gonna see they placing a limit on thermal sigma V. An entire collaboration of 200 people placing a limit on sigma V. You're still gonna see this, okay? On thermal sigma V, but it's not thermal. It's just sigma V today. You're not doing an average on the temperature evolution of the universe. Okay, first. Second is you are rely on standard model physics. Nothing else. If there's something beyond the standard model, what you're gonna get is a different answer. Okay? Okay, fine. And let's now discuss the energy flux. So the energy flux from dark matter producing cosmic rays, neutrinos, whatever, should be proportional to, well, if it's, then you have to define, it's for annihilation. I'm going to assume it's for annihilation. Annihilation of dark matter pairs. Then let me revisit this one. I have to assume that that is dark matter standard model interaction. Beyond gravity, okay? If it's just gravity, then there is no flux. Okay, so I'm assuming that dark matter does interact with standard model particles. Do you guys know here in the room why is a reasonable assumption that I should say, okay, that could be dark matter interaction with standard model fermions? Why is this a reasonable assumption? Yeah, it's definitely, yeah, it's impossible. Okay, it's from detection, but why is a reasonable assumption, theoretical assumption? Why is this a theoretical reasonable assumption? Yeah, exactly. So he answered. So the reason is we started the whole thing discussing the relic density. And the way to compute the relic density was assuming that dark matter could interact with standard model particles, right? And they were in thermal equilibrium. Even if they were not in thermal equilibrium, but they would interact with standard model particles, and that would determine the freeze out and so on. So if you assume that dark matter particles were in thermal equilibrium, then it's a consequence of that, that dark matter might indeed interact with standard model particles today. At a different rate, but still interact. Okay? Because we computed the relic density comparing the sigma v, the rate, with the expansion rate. The expansion rate is cosmology. The rate is the annihilation of two dark matter particles into standard model particles. So if that happened in the early universe, it could happen today at different temperatures, but the cross-section would still be there. Okay? Not necessarily be the same, but the interaction will still be there. Make sense? So if there was not thermal equilibrium, no thermal equilibrium, then it's tricky to say, okay, there is annihilation today, but well, if it was not in thermal equilibrium back then, means that the annihilation in standard model particles, if existed, was really, really small. In order to go outside of equilibrium, so dark matter particles were never in equilibrium with standard model particles, means that the interaction between two dark matter particles and the standard model were really, really, really small. They would not reach equilibrium. So this way it would go, this would not go back and forth. It's really small. So, but if they were in thermal equilibrium, then there's a sizable interaction between chi-chi, fermion, chi-chi. Well, if it happened in the early universe, which dictated the freeze out, so why not it's happening today? At different rates, might happen today. Okay? Especially where you have a large concentration of dark matter. Let's say in the center of galaxies, in dwarf galaxies where you have a large concentration of dark matter particles, then you increase the chances of one finding each other and annihilating. But please be careful. The overall amount of dark matter is not really changing much because these interactions are really rare. So you have abundance of dark matter, which they froze out. Remember, the freeze out means that they stopped annihilating to standard model particle fermions, and the expansion rate equaled the annihilation rate, and they froze out. There was no chi-chi fermion anymore. That's what the freeze out means, right? And we have a leftover abundance of dark matter particles. But today, in places in the universe where the concentration is really large, there might be, despite rare, a chance of those two dark matter particles finding each other and producing signals. Okay? And these are in some places, like in center of galaxies, in dwarf galaxies where the density is really large, and then you neutron stars and so on, in specific astrophysical objects. But it will not change the overall of the whole universe abundance of dark matter. It's always not meaningful effect for the overall budget of dark matter. Okay? But it still can produce a signal that I can detect. Fine? So the flux, if I have two dark matter particles, have n chi and n chi, it should depend on how strongly they are interacting, sigma v, not thermal, and should depend on what else? From this formula only, look at this. For non-relativistic particles, again, I'm assuming to be non-relativistic, then n is equal rho over m. Then I'm going to erase these two n's. I'm going to put m squared here and rho squared there. Okay? Fine. But now what I'm going to do is I have chi producing Fermi. If I'm interested in the number of gamma rays produced, so phi gamma, I want to know how many gammas are produced per annihilation. So if I produce one gamma, I have one number of gamma rays. If I produce two gammas, so even if I had one annihilation, I produce two gammas. Produce one annihilation and I produce three gammas, so I should account for the number of gammas produced. Okay? But the number of photons produced does depend on the energy of the incoming particle, or in other words, the energy of those particles in the final state, which is controlled by the initial energy. So there is number of photons, and these photons have a continuous distribution. Because if you have 1 TeV energy and you produce E plus and minus 1 TeV, you're going to produce one amount of photons. If you have a 10 TeV energy put into E plus and minus, you're going to produce a different amount of photons. Because the accelerator with a larger energy, they produce more photons. The amount of radiation you get depends on the acceleration you had. In other words, in the initial energy you had. So this number, the flux, is a function of energy as well as the number of photons produced per annihilation. Okay? Moreover, as my telescope, I'm probing a region of the sky, and I want to make sure that the flux I'm observing from this region of sky is consistent with the number of photons that Leticia observed with a different telescope, observing the same region, but in a larger volume. So I normalized by the solid angle of the region I'm observing. Okay? So this means that you have a D gamma here, or you put a D solid angle there, and then you put the solid angle here, normalization, which is 4 pi squared. Okay? 4 pi. So that's the formula for the energy flux. That's just the flux for dark matter annihilation. And the energy flux is simply, you take this formula, I mean, now we write more beautifully. The flux E omega dE equal sigma V over m chi squared 1 over 4 pi integral rho ds dn dE. And now what I did was I just integrated over the line of sight, how much dark matter there is across between the distance between me and the source. And this thing here, when I multiply by E or E squared, is called energy flux. So I then multiply by E squared here. Or I rewrite this thing here. Let me erase. Okay. So what I'm trying to concentrate in the next lectures is to derive this thing called energy spectrum. So this is from, I'm gonna write this. The energy spectrum comes from collider physics. This comes from astronomy or astrophysics. This comes from let's say, your theoretical model in particle physics. And this is your measurement, your detector. So as you see, in order to interpret the number of photons I observed in terms of some dark matter model, I need to input from astronomy, astrophysics, collider physics, in order to probe a model. For direct detection, I need an input from nuclear physics, astronomy, and the detector measurement. So it's just these two detection methods is showing to you that the search for dark matter requires multidisciplinary science. Just theoretical model building does not suffice. You do need input from different sources. Okay? So as a dark matter physicist, you should not follow some weird trends and try to undermine different areas of research, because sometimes in order to solve big problems, you need independent input from other areas which are not necessarily yours. Okay? They are also important. Okay? And I think we finished for today. We don't have any more questions. Mikhail asked for the relative. Mikhail, could you repeat the question? So I don't know in which point that happened for the relative density.
I think he was answering here.
Yeah, maybe he was. Yeah, I was answering. Okay, yes. Because of the relative density. Perfect. Okay. So if this has to do, for instance, with Guillermo asked, let's say for actions, the relative density you compute for actions has nothing to do with annihilation. Therefore, it's not natural to expect signals from gamma rays, annihilation of actions annihilating, producing gamma rays. That's weird. Actually, actions, they do have a lifetime. They're not stable particles, fully stable. They decay for a lifetime much longer than the age of the universe. That's why we haven't seen them decaying. Okay, so actions could be dark matter. To me, they're not so, that's my personal taste, and they're not so compelling because you assume them to be unstable. So it's like saying you're putting an end to the universe because you say they're unstable. If dark matter stops to exist, we are doomed. There is no galaxy, and we are going to be killed. So it's okay. Dark matter has to be stable, not cosmologically stable. It's just not natural to me, you know. So okay, you have a particle which is long-lived and it's dark matter, and you just tune it, the lifetime, to be large enough because we didn't see any decay. So I just increased the lifetime and said, no, but is this stable for us? But in 10 to 100 million years from now, it won't be stable. Everything will be doomed. It's okay. It's fine. It's consistent with data. It's okay. It's just not, you know, not so natural to me. Axions is a different story. Axions are very, very well motivated, but axions and dark matter to me is just my taste, anyways. So yes, I'm gonna post less lecture on YouTube. I just didn't post it yesterday because I had some other things to attend to. Sorry. So just to finish, that as I was saying, that we need input from other things, and the actions would not annihilate into something that I could see, but I could also observe the decay of actions into something else. Then instead of being this formula for annihilation, what you do is you replace the sigma v over mass. You replace the sigma v over mass here and put the rate. Instead of being m squared, it's just m. Because the flux, I started this formula discussing flux should be proportional to number density squared, right? I have two dark matter particles. I had two, right, to find each other. But now I had just one. If it was the decay, I just one decays. Just have n chi. So then, well, someone's entering now. N chi, and I had the interaction rate. So n chi is rho over m. So I'm going to replace this with rho over m. Okay? And what is the rate? Rate is 1 over the lifetime. So then I replace this with 1 over the lifetime. Okay? And my dn de is still here. And that's the flux. So the flux for decay would be equal 1 over 4 pi, solid angle, integration rho, dn de, and 1 over the lifetime. So the longer, the larger is the lifetime of the dark matter particle, the smaller is the flux. So if I do observe a flux of gamma rays, let's say 10, then I have to place a limit on how large tau should be to produce a flux which is smaller than 10. Because you see, as I increase tau, the number is smaller than 10, right? So I can have a dark matter particle that produces 8 events, but not larger than 10, because I observed 10 at most. Maybe I can say, no, 7 events came from dark matter, and the other 3 events came from pulsars, whatever, some astrophysical source. Okay, so I have to just impose place a constraint on the dark matter lifetime. So those are the two fluxes relevant for dark matter, either annihilation or decay. So, and you see here depends linearly on the density. There was proportional to the density squared. E squared, there's a squared here. I forgot. Right, because I had n chi and n chi. N chi is rho over m, n chi over m, so I get rho squared. So from these two formulas, the physics is fun in this way. So just from these two formulas, you see that if you want to search for dark matter annihilation, what do? You go to places where the density concentration of dark matter is really large, such as dwarf galaxies, center of galaxy. Okay? So you go to where the largest the density, that's where the place I'm going to see the result from I'm going to increase my chances of observing a flux from dark matter annihilation. For decay, it won't matter much. Okay? And it's much harder to observe a signal from decay than from annihilation, because one grows with rho squared. And you're going to see in talks, obviously in conferences, workshops, they're not going to review this and say, hey, I'm going to look at the galaxy center because of the rho squared behavior. That's all. I'm going to look at the galaxy center because of the rho squared behavior. I'm going to look at dwarfs because the rho is this amount. That is the quota number for the density. That's it. Or the mass of the halo. Okay? Okay, I think we are done for today, and I'm almost late for my lecture of electromagnetism. Okay, guys. See you tomorrow at 10. Let me turn off.